And the last lecture of this course is devoted to the multiple linear regression, which is a more interesting case of a simple linear regression. First, I will discuss what a multiple regression is. After this, I will show you how estimation and inference can be done in case of multiple regression model. In the third section, I will show you how to do hypothesis testing, and I will conclude the lecture by showing how the model can be checked for its utility. So let's go back to the example we saw in the previous lecture, and that example was about the effect of a drug on one's perception or general awareness. So we were asked to model the length of time it takes to respond to stimulus as a function of the percentage of a certain drug in the bloodstream. We have found that the intercept was equal to negative 1.1 and the slope was estimated to be 0.7. So we concluded that 1% increase in the amount of drug in the bloodstream leads to 0.7 increase in the time it takes to react to a stimulus. However, I think you will agree with me that a more realistic model should include other factors such as age, gender, time of the day the drug was taken, etc. And the moment we add the second or the third variable, what happens is that now we will be working with multiple regression model. So on this slide, you can see the general form of such a model. So y is a function of a number of independent variables, x1, x2, and all the way to xk. So we can have all the way, the number of independent variables all the way up to number k. And in this case, beta determines the contribution of each independent variable. As always, similar to the case of simple linear regression, we can split this model into two components, the deterministic and a random error component. So everything from beta 0 till last beta k is a deterministic component, whereas the error term at the end, this is the random error component. As before, y is the dependent variable and x is called an independent variable. Similar to the case of a simple linear regression, we make the same assumptions about the error term. First of all, the mean of the probability distribution of the error term is 0, and the variance of the probability distribution of the error term is constant and is equal to sigma squared. We also assume that the probability distribution of the error term is normal and the values of the error term associated with any two observed values of y are independent.